Hey everyone, how's it going? So today we'll be going over chapter 24, and in chapter 24 we'll be looking at the addition reactions on enones, and the three main reactions I'll be focusing on today are the Mannich reaction, the Michael addition, and the Robinson annulation. So let's jump right in. The first reaction I'm going to go over is the Mannich reaction. And the Mannich reaction is composed of three main steps. The first one is you're going to be presented with an amine, and it's going to be a secondary amine. This doesn't mean two quantities, this means secondary because of the prime. So a secondary amine plus formaldehyde. And we know when we have an amine and formaldehyde, they're going to react to form an imine. So it should look something like this. So if I had a secondary amine, and then I had formaldehyde, they would react through an acid catalyzed imine mechanism to give this. And this would have a positive charge here, indicating that's an iminium cation. So let's see how this goes just to refresh your idea on the imine mech. So we start off with our formaldehyde here, and because we're working in acid, we're going to protonate it first. And we always remember that protonating a carbonyl creates a good electrophile. So we have protonated it and we have a good electrophile. So naturally, the next step is nucleophilic addition by our amine. And our amines are pretty decent nucleophiles, so this makes sense. So it's going to add on now. And if we look at this over here, we have a carbon with the nitrogen sticking off and an oxygen. And we know in our final product, we just have a nitrogen. So somehow we want to keep the nitrogen and we want to get rid of the oxygen. And remember with these types of mechanisms that protonation helps groups leave, while deprotonating is what you want to do to groups that you want to stay. So if we want our nitrogen to stay, we want to deprotonate it. So we're going to get rid of this positive charge by taking off this proton. And we're going to be left with this. Now the next step is we want to get rid of this OH. And OH isn't a good leaving group by itself. So what we're going to do is we're going to protonate it to form this oxonium cation. And in order to get rid of it, we're going to have this assisted leaving by this nitrogen. It's going to use its lone pairs to come down and push off this oxonium cation. And we're going to be left with this. And, oh man, oops. And this right here is the same thing that I drew over here. So if you remember from our mechanisms, when we have a secondary amine, we usually form an enamine. And an enamine looks something like this. So normally we have this, and then a base comes, and it's going to abstract an alpha proton. This bond will swing over here and kick up this pi bond to get rid of this positive charge. So in reality, our amine should look like this. So this is an enamine. But here we don't have that double bond forming on the side, and the reason why is because we have hydrogens on both sides. So it's non-enolizable. We can't form an enolate like we did here. And because of that, we're stuck with this positive charge. This is very good. This is part of the reason why the first step of the Mannich reaction always uses formaldehyde. It can't use any other carbonyl. It's because we want there to be a positive charge on this compound. And what does a positive charge mean? It means it's a good electrophile. If I get rid of it by doing this conversion, then this isn't as great of an electrophile. In fact, it becomes a nucleophile instead. But here, this is pretty electrophilic because this bond resonates, and then we'll get this positive charge on the carbon. So in this first step right here, we combined our secondary amine plus formaldehyde to form an iminium cation. And this iminium cation is a good electrophile, as I wrote up here. So then the next step is, if we formed a good electrophile, we should probably add a nucleophile to it. And that's exactly what we're going to do. So here's our nucleophile. We have this, this benzene plus a ketone group over here. I think that's called the acetophenone. And what's going to happen now is it's going to turn into its conjugate enolate base, as we show over here. And what it's going to do is it's going to act as a nucleophile now. So let's write that in. We created a nucleophile from our enolate, and we use it to attack our electrophile we created in the first step. Remember, this right here is what we just created over here. It's the iminium cation. So negative charge attacks positive charge, and we should get something like this. So this is almost our final product. The only thing is we have this hydrogen here, so that's an easy fix. We could just deprotonate it, and we're left with this, the Mannich base. So let's look up at our steps of, so far. We finished step 2. Our iminium cation reacts with the enolate in a nucleophilic reaction to produce our Mannich base. So this is sometimes when the reaction ends, but in other cases they might say, okay, once we form this, let's add heat and base. And the thing you need to know about the Mannich base is that it's very susceptible to thermal elimination. And when we had heat and base, we'll eliminate the nitrogen group to yield an enone. So let's see how that happens. So over here, I just redrew this Mannich base that we had. And it's a bit easier to see now. So now let's say your professor, he gives you the reagents for these first steps, and then he adds heat and base at the last step. What's going to happen? Well, what this base is going to do is it's going to abstract this proton right here, this alpha proton. But instead of swinging to the left like we expected to, it's actually going to swing to the right. And because of that, we need to kick something off. So we're going to kick off this nitrogen group. And it's probably just going to grab a proton from somewhere in solution. That's not important. But what we're going to be left with is an enone product. So let's see what that looks like now. So the enone is alpha beta unsaturated. So this is the carbonyl carbon. The one next to it is alpha, and the one further away is beta. So it's alpha beta unsaturated because there's an alkene here. This nitrogen leaves, so you're just going to be left with this nitrogen. It's going to be protonated, floating around in solution. So this is your final product. So if you know that the thermal elimination of a Mannich base yields an enone, this will be easy for you to do in your head instead of working through the entire mechanism. But this is just the premise of the Mannich reaction. So let's do a practice problem now. Here we have our ketone, and we know that when we do a Mannich reaction, we're going to have a ketone turns into our nucleophile, right? Because the base is added to it. And the formaldehyde that we have here and the secondary amine are used to form our iminium cation, which is our electrophile. So let's just pretend like we formed our iminium cation. So we should be left with this. And our cation has a positive charge on the nitrogen, making this a very good electrophile. And let's say now that this aldehyde that we have here gets deprotonated. It can't be enolized from the right side because there's just a hydrogen here. There's no alpha carbon, but here we can. So we put our lone pairs here, our negative charge, and it's going to come in and it's going to attack this electrophilic center and push up this pi bond. So what we should get, let's see, let's draw it out and see what we get. So I'll use purple to describe this bond that we just formed, this bond right here. So that will be right here. And so from this carbon, there's another carbon and nitrogen. So from this carbon, there's another carbon and there's a nitrogen. And the nitrogen has two methyl groups sticking off. And let's just CH2. So CH2, nitrogen with two methyls sticking off. Okay, cool. So that's our Mannich base that we just created. However, if we look at our arrow, on the second line, there's 50 degrees Celsius. And if you guys know your Fahrenheit to Celsius conversion, that's actually pretty warm. And what that means is that we're adding heat. And remember, the third step, the third optional step of a Mannich reaction is the thermal elimination. So what we're going to do is, let's draw it in again. So let's say there's just this alpha proton sticking off here. Our base is going to come in. Let's use a different color. So it's going to grab this proton. This bond is going to fall back not to this side, but to this one. And it's going to kick off this secondary amine, which is going to grab a proton in solution. So what you're going to be left with is the enone product. and this is your final product. So this is basically how you do a Mannich reaction. So it's not too complicated. The one thing I want you guys to take away from this is that a Mannich reaction, it seems like a pretty useless reaction. Okay, we created this, but it seems like such a weird compound, and it is. But the third step is when things get more important synthetically because you create an enone. And the rest of this entire unit is about enones. So we'll see all the cool, novel things we can do with that and how this Mannich reaction can be a useful synthetic precursor. One cool thing I want to show you guys I saw online was that the Mannich reaction actually has some pretty interesting applications to pharmaceutics. So if we start with this acetophenone and we do a Mannich reaction, we create this compound, and then you can get rid of this carbonyl by forming an OH and then converting it to a chlorine using SOCl2, and then this strong nucleophile will kick off this good leaving group in an SN2 reaction, and this is how you create this compound over here. This compound is more commonly known as Prozac, which is an antidepressant, and it works by acting as an SSRI, a selective serotonin reuptake inhibitor. So like when you have a synapse, usually your synapse that releases serotonin will release it into this cleft, and it'll bind to these serotonin receptors. And serotonin is, it's like a feel-good hormone. So you want more of it if you want to be happy. And in case of people who are depressed, they don't have as much or they want more. So what they do is they prevent the reuptake of the serotonin back into the neuron. So there's more time for it to hang around here. So the Prozac blocks this channel, sort of. So now people have this better like feeling of happiness because there's more serotonin just staying in the synaptic cleft. All right, so let's go into what an enone is. We just saw that our Mannich reaction can form an enone through our third optional step, which is the thermal elimination. And this is what an enone is. Sometimes you'll hear it referred to as an alpha-beta unsaturated ketone. And what that means is that this carbon right here, the one next to it is the alpha and this is the beta. They're both unsaturated because they have a double bond. And that's just a synonym for it. Let's look at the resonance for this because it'll tell us something interesting about these reactions. So simple. Let's just first push up this pi bond we have over here. And what we should be left with is this. And there should be a positive charge on carbon 2. When we work on an enone system, sorry, I forgot to mention, was that there's four sort of numbers we use. Oxygen is 1, this carbon is 2, this is 3, and this is 4. We'll get more into that a bit later. But we see that there's a positive charge on carbon 2. So now let's push over this pi bond over here to fill up that positive charge. So let's see what we get now. Oh. Stay on page. Oh man, what is this? Alright. We should get something like this. So here we also see that there's a positive charge, but it's moved over to carbon 4. And what does that tell us? That tells us that in an enone, there are two carbons that are electrophilic, carbon 2 and carbon 4. But there's one that's more electrophilic than the other, and that's carbon 2. Let's see if we can look at our resonance structures and figure out why that is. Well, if we look here, we know that the one that's the better electrophile from these two will be the more important resonance contributing structure. And the way we determine that is we look at which one is more of a stable contributing structure. And we know that we want to keep opposite charges closer together because they're more attractive, in the same line of reasoning that we want to separate like charges. So if I had two positive charges, I want to separate them. Here, because they're the same, I want to keep them close together. Because of that, this contributor over here is more important than this guy. So in this blend of structures, it's going to spend more time over here than in this third structure. And because of that, this positive charge will reside on the second carbon more often, making it a better electrophile. So the main takeaway I want you guys to get from this is that carbon 2 is very electrophilic because this resonance contributor is more important since these charges, these opposite charges are close together, while carbon 4 is it's a moderate electrophile. It has a positive charge, but isn't that great because these two really attractive charges are far apart. So there's a overarching theme I've realized in Orgo 2 looking back on it now, and what I've figured out is it's like attacks like. So if I have a very strong nucleophile, it's going to attack the very strong electrophile on carbon 2. But if I have a moderate, alright base, alright nucleophile, it's only going to attack the moderate electrophile on carbon 4. So I made this little table for you guys, so it's like a cheat sheet for your 1,4 versus 1,2 enone additions. And most of your nucleophiles will attack 1,4, but a few of them will attack 1,2. So it's better to just memorize the 1,2, and then you can see the rest of them will just be 1,4. So remember that carbon 2 is a super good electrophile. And because like attacks like, then we know that these nucleophiles have to be super good. And we see that they are because they're Grignards, organolithiums, and hydrides. And if we look at our pKa table over here, let's just quickly orient ourselves. The highest pKa is on the top while the lowest is on the bottom, which means the worst acid is up here, also known as the best base. And because of that, our alkanes, our alkanes right here are very bad acids. They're pretty bad. But if I deprotonate them, similar as if we're doing MgBr, creating an organolithium or a Grignards, this is the same thing as the conjugate base, and that's a very good base. So that's one of the reasons why it preferentially attacks carbon 2 is because it's a strong base. The other one we want to look at is hydrogen, because in our lithium aluminum hydride or sodium borohydride, we have our atom in the middle, and it's surrounded by 4 hydrogens. And when these hydrogens attack an electrophile, they don't just go as a neutral hydrogen. They're going to leave as a hydride anion. And the hydride anion is basically just the conjugate base of hydrogen. And we know that since hydrogen is pretty high up on this table, it's a bad acid, but it's a pretty good base, which makes this a good base. One important thing to note is that not all organometallics are really good bases. Here we see 2 of them are because they attack the second carbon, but one of them is 1,4, and that's the one you have to watch out for because it's a tricky one, and of course the tricky ones are the ones always tested. So the organocuprates, also known as your Gilman reagents, they attack 1,4, and that's just a distinction you guys have to learn. And with organocuprates, you have to be very careful of tandem addition, and we'll go over a sample question of what tandem addition looks like, but you guys have seen it before. And then the other nucleophiles that can attack 1,4 are cyanides, amines, thiolates, alcohols, waters, halides, and azides. And those are much lower on this pKa table that I haven't fully drawn out because it's just not as important. But if we look here, I guess where you can make the distinction between 1,2 and 1,4 is along this line right here. Because above it we have our hydrogen and we have our alkane, and we know those are attacking 1,2. But we know our amine attacks 1,4, so that's sort of like your separating line, because our amine attacks 1,4. So let's look at what the mechanism of this looks like. So if we attack 1,4, we know that, let's just orient ourselves. This is our enone, and this is our nucleophile. So this is oxygen 1, carbon 2, carbon 3, and carbon 4. It's going to attack, push off this double bond, and kick up this pi bond. And what we're going to get is this sort of enolate anion. And now, because there's no electrophile sitting, it doesn't want to attack anything, so it's just going to protonate itself to form the carbonyl. So here we notice our nucleophile added into the 4th carbon, and this double bond that was originally here is just gone now. If we have direct addition, also known as 1,2 addition, our nucleophile is not going to care about this because it's not as strong of an electrophile. So our strong nucleophile will attack this strong electrophile at carbon 2, push up this pi bond, and we should get an O-, which is going to get protonated to form an alcohol. So these are your 2 different types of additions you can have with enones. So let's go over 5 quick practice questions. I urge you to pause the video for a second, try and figure it out, and then we'll jump into it. Alrighty, I hope you guys got a chance to give those problems a try, and let's see what they are. It's not too bad. Let's draw purple. So, we know we have our enone, because oxygen 1, carbon 2, carbon 3, and carbon 4. And we know our cyanide isn't that great of a base. It's pretty good, but it's not as strong as it could be. So what it's going to do is it's going to attack 1,4. So it's going to attack this carbon and push up this pi bond and push up this. So we should get a final product of 1,4, also known as conjugate addition. So this should be your answer for number 1. Alright, let's go into number 2 now. So we have a thiolate here. And what our thiol will do is it's an alright nucleophile, but it's not as good as the organolithium or the Grignards or the aluminum hydrides. So we're just going to attack 1,4 once again. So this acts as a nucleophile and it's going to attack 1,4. Here it's the same thing. Our amine is alright. It's not the best nucleophile in the world, so it's going to attack the moderate electrophile site. So there's 3 carbons on each side, so 1, 2, 3, 1, 2, 3. Now here, this is a tricky one. Let's go back up to the table. We were presented with an organocuprate. So organocuprate is actually 1,4, not 1,2, and I told you, beware of tandem addition. So let's see what that means. So the first thing that's going to happen is this organocuprate will attack 1,4. So you should see it coming in and attacking here. And let's just push this bond up. So negative charge on this carbon, and we just added on a phenyl group. And remember, even though there's 2 phenyl groups in your organocuprate, only one of them adds on. So now, normally, we form this carbanion just like we do in all these cases, but here it gets protonated because there's no electrophile to attack. But here there's an ethyl bromide. So what this carbanion is going to do is it's going to attack this electrophilic center and push off this good leaving group. And this is the tandem cuprate addition that we've been talking about. So we should be left with 1, 2. This should be our final product. And now here, this one's also a bit tricky. This is similar to an enone. Let's draw out what it really looks like. This behaves really similarly because it's similar as if this was just a carbonyl sitting here. So we treat it as if it's an enone. And what's going to happen is we have our Grignard's reagent. So if we look at our table from above, we know that the Grignard is very strong, so it's going to attack 1, 2. So let's pretend like it comes in here and attacks this. Oh wait, whoops, messed that up. It's going to attack here. And that's going to kick up this pi bond over here. So this negative charge gets protonated, and we have our ethyl just sticking off over here. And now we have acid. And if you guys remember from your iminium unit that if you add acid to an amine, it gets hydrolyzed to a ketone. So what's going to happen is the water is going to come in, and it's going to attack over here and push up this pi bond. So we should be left with whoops. Something like this once we have all the protonations and things done. And what we're going to do now is we're going to protonate this NH2 again to form a good leaving group. So this should be an NH3 plus now. Oh, ignore that. And now our lone pairs on the oxygen will come down and kick off this. And this is just the mechanism to show you guys that your final product should be this. It should convert your cyanide to a ketone. So remember, this acts as an enone, and your Grignard is going to attack 1, 2, and then afterwards your acid is going to hydrolyze your cyanide back into a ketone. Alright, so now let's get into a cool biochemistry application of your 1,4 addition to enones. So once again, I'm showing you guys this diagram. This is your glycolysis in the beginning. It breaks down your glucose into pyruvate, and pyruvate then converts to acetyl-CoA, which enters the Krebs cycle to provide high-energy electron carriers. And these electron carriers can be used by the electron transport chain to create a proton gradient, which can be used to create ATP. Now, the part we are interested in is over here. We are interested in the conversion of citrate to isocitrate. However, to understand why it's necessary to do this, if you look at the prefix, iso just means an isomer. So there's nothing being added, nothing being removed. It's the same molecule, just sort of switched around. And what's the need to isomerize citrate if, why is it better? So in order to understand, we need to look at 2-oxoglutarate, which is also known as alpha-ketoglutarate. So let's look at what they look like structurally in terms of Fischer projections. So over here we have citrate. That's what was over here. And then isocitrate is this third structure. And 2-oxoglutarate is known as alpha-ketoglutarate. So that's this fifth structure over here. So let's just get an overview of what's happening here. In our TCA cycle, there are two things happening. One is that we're forming high-energy electron carriers, so we're converting NAD plus to NADH. The part we're concerned about here is we're also stripping away carbons. So here are 4-carbon oxaloacetate and 2-carbon acetyl-CoA combined to form a 6-carbon citrate. So here there's 1, 2, 3, 4, 5, 6 carbons. And as we progress through the cycle, our alpha-ketoglutarate only has 5 carbons, and our succinyl-CoA has 4 because we want to regenerate this 4-carbon oxaloacetate. So we're removing carbons here. And if you guys remember from your previous orgo lectures, one of the reactions we learned to remove carbons is decarboxylation. And that is exactly what happens here. So we see from citrate to alpha-ketoglutarate, there's only 1, 2, 3, 4, 5 carbons. And the one that's missing is the COO-. So that makes sense. We are decarboxylating in this last step. But if you remember, one of the precursors for decarboxylation is you need a beta carbonyl because it's beta decarboxylation. You can't just decarboxylate anything. Otherwise, this would come off and this would come off. So we need a carbonyl that's either here or here. But right now we don't have that. Well, if we have an OH, we can always oxidize it to a carbonyl, right? But here it's not in the right location, so we need to shift it over one. So that's exactly what we do in isocitrate. We shift over this OH to the beta position. And then we oxidize it using NAD+. You can think of it like PCC from orgo. It's a similar function, NAD+ and PCC. And what it's going to do is it's going to oxidize it to a carbonyl group, which allows beta decarboxylation to occur in this last step. So now you get an idea of why this reaction is actually necessary. But let's look into the biochemistry and the orgo behind it a little bit now. So the reaction that catalyzes this is it uses a 1,4-enone reaction, and the intermediate is cis-aconitate, and the enzyme is called aconitase. So let's see what happens here. It's going to be a pretty big pathway, so just have patience, but it's pretty interesting. So this is our citrate over here. Let's just orient ourselves. Our citrate has 5 carbons, 1, 2, 3, 4, 5, and it has 3 carboxylic acids. 1 at the first end, 1 at the other end, and 1 in the middle. Here we have 1 at the end, 1 at the end, and 1 at the middle. And 5 carbons here, plus a 6 carbon. So that's citrate. Now, citrate has to somehow create cis aconitate, and the mechanism behind that is E1CB. Now, if you guys remember E1CB, what happens is first, let's write it out. In E1CB, first the base deprotonates alpha carbon, and then in the second step, carb anion eliminates OH. So let's see how that happens here. Well, a basic side chain on our amino acid is going to come in and it's going to deprotonate this alpha carbon because here we have a carbonyl, so this is alpha to it. And what we're going to get is a carb anion on this carbon. It's going to resonate over here. Now, in the second step, we know that carb anion just eliminates this OH, so this negative charge is going to come down and just kick off this OH even without protonating it because we're in basic conditions here. So this is the E1CB. And because of that, we form this aconitate. And your professor's note are missing the word cis here because this is a cis double bond. So we form cis aconitate through an E1CB mechanism. What happens first is we deprotonate the alpha carbon, and then this carb anion is used to kick off this OH, even though it's not a good leaving group. So now we have our aconitate, and we need to somehow convert it to our isocitrate, right? So we form this through E1CB. Now we need to get this somehow. We need to add an OH back in. So we're doing some form of nucleophilic addition. Well, if you look at it, we have an alkene, and right next to it is a it's like basically similar to a ketone, but it's a carboxylic acid. So this can be thought of as an enone. And we can do a nucleophilic 1,4 addition with water to our enone to form our isocitrate. So let's see how that happens. So now that we formed our cis aconitate, which is our enone, our water is going to come in and do 1,4 addition. See how this looks similar to a enone even though it's a carboxylic acid at the end? So it's going to do 1,4 because this nucleophile is pretty crappy. It's not that good, so it's going to attack the crappy electrophile site. And it's going to push up everything to form an O-, and we know that we just have to protonate it because there's no electrophile sitting around. And what's going to happen is we're going to form our isocitrate. So let's just summarize what happened. We started with our cis aconitate, and our water does 1,4 addition to the enone to form our isocitrate. So I hope that gives you guys some clarity into how we form isocitrate and why it's important to move around that OH- in order to do decarboxylation at the end. Alrighty, so now let's go over the next reaction on our list. This is Michael addition. Michael addition is the reaction of an enolate, which is your nucleophile, to an enone, which is an electrophile. And this is a 1,4 addition, and we form a product. But the product has a very specific functional group, and that functional group is a 1,5-diketone. And this looks like a lot of numbers, a lot of words, so let's just understand what that means with an example problem. So over here I drew a very simple Michael addition. And here we have our nucleophile soon to be. This is our enone, so this is our electrophile. This NaOH is going to be used to create an enolate out of this. So what we're going to get is we're going to get a carb anion on this alpha carbon. So here's the nucleophile, here's the electrophile. Remember, if it's not a Grignard, if it's not an organolithium, and if it's not an hydride, it's going to attack 1,4, even if it's an enolate. So it's going to attack this fourth carbon, and it's going to push this guy up and push this up. And what we're going to be left with is this product. This product is a 1,5-diketone. So if we look at it, carbon 1, 2, 3, 4, and 5. So 1 and 5 both have ketones on them. Alright, so it's a pretty simple reaction in that sense. I'm going to give you guys 2 practice problems, pause the video, and take a chance to do them, and then we'll work them out. Alright everyone, so let's jump back into it. We know our NaOH is going to act as a good base, so it's going to create a carb anion over here. And this seems like a very complicated molecule, but in reality it's just an enone. It just has some crap sticking off at one end. So we could just, for example, think of this as an enone. And we know that this is carbon 2 and this is carbon 4. Our enolate attacks to the 4th position. So it's going to attack here, and then it's going to push everything up. So let's see what we're left with. Oh yeah, excuse my poor drawing, sorry. So this is what we had originally. Now I'll use purple to draw the bond that we just formed. And let's use black to draw the thing that we just started with. So it should look like something like this. And this is a 1, 2, 3, 4, 5. So 1,5 diketone. So that's how you know we did it correctly. So there's a way to check. And let's use that same methodology here. But now here, the interesting thing is, although these two look similar, here it was an electrophile because it's an enone. Here, this is going to act as a nucleophile. Our NaOH is going to deprotonate this at the alpha carbon to create a carb anion. And that's going to attack 1,4 on this enone, push up this pi bond, and push up this pi bond. And let's see what we get. So let's use purple to draw the bond we just formed. And I'll use red. So this should be your final product. Alright, so far we've went over what the Mannich reaction is, and we know that the Mannich can be used to form enones, and we went over the Michael addition, which forms 1,5 diketones. So now let's go over the third reaction. The third reaction is known to be the harder one. This is the Robinson annulation. And this is the one I know that everyone gets tripped up on because they either miscount carbons, they get confused by the mechanism. So we're going to take it step by step and understand every part of this reaction. So the way this Robinson annulation works is it's actually just a condensing two reactions we've seen before. It's a Michael addition, and remember, a Michael addition is an enone plus an enolate to form a 1,5 diketone, and an intramolecular aldol condensation, which is two carbonyls to form a beta hydroxyketone. So when we add these two reactions together, we can form two fused 6-member rings. And if we think about it, let's see what a 6-membered ring fused together looks like. It looks something like this. And if you guys remember, if you see something like cholesterol, actually, it looks something like this. So you can see how these fused 6-membered rings are very important for biological drugs or even molecules in our body. So this is a very important reaction that still has synthetic applications today. So I'm going to do a quick overview of some reactions that are important before we get into this, so you guys have that very strong foundation to tackle these problems. The first one I want to go into with you guys is the aldol condensation. So with the aldol condensation, here we have a very simple one. Two aldehydes, and we know that we're going to form an enolate here. It's going to attack this electrophile and push up this bond, and you should form this. This right here, this is the bond we just formed. So remember, the product of our aldol formation is always, oh, I should draw a hydrogen here, my fault. The product of the aldol formation is always a beta hydroxyketone, or aldehyde, it doesn't matter. So in this case, it would actually be an aldehyde. And here, if we add heat to this aldol formation product, we can get an aldol condensation. So water will actually leave this, this intermediate. So we can draw water coming out. And what we should form is an enone. And if you guys remember from the previous video, this precedes by an E1CB mech. So what's going to happen is some base is going to come along and grab off this proton and push this over here to form a carbanion. So it's going to look like this. And what this carbanion is going to do is it's going to do an E1CB reaction. So it's going to come over here and kick off this OH minus. So what that will leave you with is this product over here. So there are two ways now you guys have seen to create an enone. Two ways to create enones. The first one being aldol condensation, not just formation, it has to do this condensation step as well. The other one in this video is the Mannich reaction. So just keep those two in mind. Alright, so now we saw a simple version of the aldol condensation. Now let's go over a more complicated intramolecular aldol condensation. Here we have a pretty long molecule, and if we add base to it, we know we're going to do aldol within itself, so this is intramolecular. So if I count from here, 1, 2, 3, 4, 5, 6, I can either form an enolate here or here. If I form it here, I'm going to form a 4-membered ring. That's pretty unstable. But if I form an enolate on this carbon, it's a 6-membered ring. That's pretty stabilizing. So let's form the enolate here, and it's going to attack this electrophilic center and push up this bond. So you should be left with this over here. And if we look at it, I'm trying to figure this out. This is the bond we just formed. And this oxygen on this one is this one over here. So this is what we ended up forming. And now if we add heat, we know we're going to form an enone through an E1CB mechanism. So we should get this. So why did I show you this intramolecular one if I already showed you a regular one? The reason why is I want you guys to understand that in order to form a 6-membered ring, well, why do I care about 6-membered ring? The reason why is because in Robinson annulation, the product will be 2 fused 6-membered rings. And because we're working with an aldol condensation in the second step, we know that to form a 6-membered ring, we need a 1, 2, 3, 4, 5, a 1,5 diketone. So main takeaway, you need a 1,5 diketone to form a 6-membered ring. This should ring a bell, because in the previous reaction we learned, we knew that Michael addition actually creates a 1,5 diketone. That's why these two reactions are paired together. The Michael addition creates the 1,5 diketone for our aldol condensation to use to create the 6-membered ring. Now that sounds like a lot. We'll get into the nuances later, but I just want you guys to understand why these reactions are paired together. And let's just quickly review what the Michael addition is. The Michael addition is when you have an enone and you have our nucleophile over here from the enolate. It's going to attack the 4th carbon and it's going to form a 1, 2, 3, 4, 5 carbon diketone. So let's now go into what the mechanism looks like for a Robinson annulation. So this is what we're going to be going over. It's pretty complicated, but I'm sure you guys can get through it with me. We'll break it down step by step, so don't be too intimidated. Alright, so the first step whenever you have a Robinson annulation is you're going to already have a 6-membered ring formed. Remember, the Robinson annulation creates 2 fused 6-membered rings, but you need to start off with 1 6-membered ring to begin with. So this is the one we start off to begin with. When we add base, we're going to form an enolate on our cyclohexanone. And this is going to serve as our nucleophile for your Michael addition. Remember, your Michael addition is your enolate nucleophile, nucleophile plus your enone electrophile. So we already created our enolate nucleophile in the first step. Now here, we're already provided our enone electrophile. Okay, that makes it pretty easy. So what's going to happen is our enolate attacks our enone at the 4th carbon, not the 2nd. The reason why? Our enolate's a pretty crappy nucleophile compared to the really good ones. So it's going to attack the crappy electrophile site. And here we form this weird intermediate. Now, remember, we're trying to form 2 6-membered fused rings. So we know somehow we have to connect over here. But if we look at it, our enolate's on this carbon, not on the one we need. So we need to somehow protonate this and get rid of it, and then shift the enolate over. So in our first step here, we get rid of this enolate on the top by adding some acid, I guess you could say. So here we have a pretty neutral compound. Now if I add base again, and we can choose which one we wanted to prefer due to like thermodynamic and kinetic temperatures. So if I wanted to prefer this side, this is going to be your kinetic product. So you should probably use cooler temperatures, like -78 degrees Celsius. And what's going to happen is you form this kinetic enolate, and now we have two carbonyl groups, right? Over here and over here. And if you look at it, it's 1, 2, 3, 4, 5. A 1,5 diketone can do intermolecular aldol condensation to form a 6-membered ring. And that's exactly what's going to happen here. Our enolate is going to come down and attack this carbonyl group, and we form this 2 fused 6-membered rings. We're going to protonate this O- to form our beta hydroxyketone, remember, which is the product of the aldol formation. However, if we add heat to it, then we can do our aldol condensation and get rid of water to form this enone. So this is your Robinson annulation. We created our enolate in the first step, which attacks our enone to create a 1,5 diketone. This 1,5 diketone can then do intermolecular aldol condensation to form the beta hydroxyketone, which is the product of our aldol formation, and then adding heat and base should revert this to the enone form through condensation. Sorry, that was a lot to say. Yeah, so that's pretty complicated, I understand, but you guys got through it. And these are the 4 component steps that we needed to do. I just went over them, so you guys can read it and take notes. But I'm glad you guys got through it. So for the probably like 5% of you that have continued watching up to this point, saw a pretty cool meme. And this is a pretty cool application of Robinson annulation. We have here is we have a nucleophile we can form, and it's going to attack this enone, and we get this formed ring. And what we're going to do with this bicyclic ring is we can create estrone. Now, estrone is a common precursor for synthesis of birth control. So you can see all these organic chemistry reactions are still used today, and they're used for a lot of, I guess, good options for college students, right? So, yeah. All right, so now let's get into the practice problems we have. I put a lot today because there are a lot of concepts we have covered, and they're pretty tricky, so I want you guys to be able to hammer this in. So the first one over here, I'll give you a hint. You should think about the first reaction we covered today, and remember what that reaction creates. Here, this is the addition to an enone. Figure out what side it attacks. Same thing here. This is just to test if you guys actually watched the video or not. Number 5, it's the same thing, addition to an enone. Same here. Now here we get into Robinson annulation. This is a multiple choice question. And here I put a synthesis from my year in organic chemistry. And in this one, it's a very tricky synthesis, but it involves all 3 reactions we did today. So if you guys can get it, then you know you have this material down cold. So thanks for watching, guys. If you have any questions, feel free to shoot me a message or write a comment on the video. And stay safe, everyone.